Okay, so thank you for the introduction, and I'll start by thanking the organizers for the invitation to speak here. I must also say that in some sense, the local speaker of the conference, right? Since no one was there from TIFR, I am from Mumbai, IIT. So the local speaker of the conference, and I must also say that, I do come here frequently, and I have spent 2.5 very memorable years here. So it's good to be back, and the results that I'm going to present, in some sense, originate from my years here, joint work with Deependra Prasad and also work with Rajan. Okay, so I must also say that I said I am the local speaker of the conference, certainly geographically from Mumbai. I am also the local speaker in the sense the talk is local representation theory. So we will, so this will be a talk in local representation theory. Throughout we will have a p-adic field. So F is a finite extension of QP. And in two of the talks in this conference, Akshay Venkatesh and Zinwen Shu, they were about period integrals, and it was stressed in both the talks several times that period integrals are closely related to L functions. That's why one studies them. And this is so distinguished representations. The notion of distinction is exactly the local analog of the period integrals. So period integrals, one was studying period integrals in order to understand L functions. Similarly here, naturally, when one studies, of course I'm going to introduce, I'll have the definition soon. And once we, the corresponding notion of period integrals here will play a role in so L functions are not that difficult in the local theory, but the corresponding thing will be the gamma factors, and it will have close connections. So the notion of distinction locally is a very simple concept, very easy to introduce concept. So let G be any group, meaning a p-adic group. It could have been any group for this definition, it doesn't matter. And distinction is with respect to a subgroup, so H is a subgroup of G. And let's take pi to be. So the space of pi also I will denote by pi itself. Let pi be an irreducible representation of G. For p-adic groups, we will naturally look at irreducible admissible representations. And so distinction is with respect to H, and we say that pi is distinguished with respect to H if this space home H pi 1. So these are the intertwining maps from pi to, this is the trivial representation, and this is non-zero. So it's an innocent looking definition. One just says that pi is distinguished with respect to H if there is an element here. This is non-zero. So if there's an element here, that means L of pi HV is L of V, V in V, and H in H. Right? It's sometimes it's useful to look at a slight variation of this, where you may take a character of H instead of the trivial character, and one might look at home H pi chi. So if that is non-zero, one says that pi is chi distinguished with respect to H. So as you can see, the definition does not have much in it. It's quite an innocuous, innocent looking definition, and one could have defined it for any group and any subgroup. But in the Langlands program, or in the words of Akshay Venkatesh, the relative Langlands program, which is this, So since we are in the local situation, let us say relative local land-length program, which is the study of distinguished representations. It becomes important in land-length program because it's closely connected to, so this is the basic theme, distinction, the property of being distinguished. Distinction is closely connected to what I will call base change. So this is land-length functorial lifts. Which of course is not so easy to introduce, right? I mean, in order to introduce base change, I need to, set up some notations, definitions. I mean, it's not so easy. So this kind of a simple looking thing is closely related to base change is the basic theme in the subject, and that's why this thing becomes very important. So a bit more precisely, there is what is many people call this as Jacquet's philosophy, Hervé Jacquet. So G is a p-adic group, as earlier, and H is not any subgroup, but the fixed points of an involution on G. So in this special case, so you have G and H fixed points of an involution. It is predicted that they will be a related group G prime. It's believed that there is a related group G prime, so that distinction with respect to H is characterized by base change from G prime to G. So this is the general philosophy, and that's why this topic is of much interest. So let me come to a specific situation. Finally in this talk, the groups will be as simple as GLN and maximum SLN, nothing more. Let me come to a specific situation, a basic case of this picture, a group and fixed points of an involution. So if G is a quasi-split group, then you consider E over F to be a quadratic extension, degree 2 extension of p-adic fields, and the and you consider G to be the E points and H to be the F points. So the involution being the Galois involution, right? So let me denote sigma to be the non-trivial element of the Galois group. And maybe for future purposes, let me also denote omega to be the quadratic character of F star associated to the extension E over F. Okay, so in particular, so when G is like that and H is the fixed points of the Galois involution, this philosophy is, Jacquet's philosophy is made somewhat more precise. Philosophy is made more precise by somewhat recent conjectures of Dipendra Prasad. So the thing to keep in mind is whenever distinction is there, functorial lifts are going to come in various ways, and that's the broad picture. So there are some precise conjectures. I won't state it very precisely, but let's state one or two parts of it. So this is the picture, and in these conjectures corresponding to this G and H, there has to be a group G prime, right, from which representations are going to base change. That G prime is made precise in these conjectures, so it's called the opposition group. So corresponding to this involution, there's the opposition involution, and it's the fixed points of the opposition involution. That's made precise. There's also a character. Maybe I'll denote again by omega. Doesn't matter. It's not that omega. a character, okay, let's say chi, of degree, a character of h, of order less than or equal to 1. It's either the trivial character or a quadratic character. And this, so G prime depends on the algebraic group G, and the character chi depends on G and E over F. Okay, so these two things are constructed, and then the conjecture would say that if pi is a representation, so let's say pi is a representation of G, then if pi is distinguished, meaning I will not say H distinguished, it's understood, H is fixed. So if pi is distinguished, then it is conjugate self-dual. My handwriting is visible at the back, no? It's not very small, right?
Right darker.
Right darker, okay. Yeah, try. So what is conjugate self-dual? Conjugate self-dual meaning pi is the representation, you take its contragradient, and that is isomorphic to pi twisted with the Galois involution sigma. So self-dual up to Galois conjugacy, I mean with Galois conjugacy, so pi dual is pi sigma. And how is it related to base change? So in general, for groups other than GLN, when one studies representations, they come in what is called L packets. Corresponding to a Lagrange parameter, there will be a packet of representation. So let's take a packet of pi, L packet of pi. And the conjecture says that this will be, this is a base change of an L packet of representations of G prime. So by G prime I mean G prime of the F points of G prime. I'll continue to denote G prime equal to G prime of F. Okay, so if distinction is there, then you have conjugate self-duality, and it will be a base change from the opposition group. And another part of the conjecture would say that if pi is such that a slight converse of this, its L packet is base change from G prime, then is pi distinguished, right? That will be the converse. And the answer here is also assume, so suppose pi is base change, and also pi has, let us say pi is generic. It has a Whittaker model, generic meaning has a Whittaker model. With respect to, so Whittaker model is with respect to an additive character, with respect to a character of the unipotent radical of the Borel, and it should have the property, so n is the unipotent radical of the Borel, it should have the property that it's trivial on nf. So if pi is, if the packet of pi is a base change from the opposition group, and also if pi is generic with respect to such a distinguished character, not just any character of the unipotent radical, but any by nf, which are trivial on nf, then pi is distinguished. So a kind of a converse to one. And then there is, this is the real part of the conjecture which I won't state. One is interested in home H pi 1, right? Distinction means this space is non-zero. A natural question to ask is how big is that space? How many such invariant linear forms are there? So one is interested in the dimension of this space, and there is a precise formula to compute that. So I will state it in our result for SLN, we will state the precise formula, but in this formula also base change information appears. Okay. just to get the picture clear, let's take the most well understood example. So the most well understood example is of course GLN. Example is GLN. So here, of course, all these the results that I am going to state were already known before the conjectures being made, and all these things are true. So let me recall some of the famous results. So the results that I will state are due to Flicker, 1991, and Nadir Matrange, 2011, and Chungpang Mok, 2015. Conjecture was made roughly in 1516. So what are these results? Flicker would say that this part is true. So if pi is, by the way, for GLN, L packet is a singleton. There's no real L packet, it's just a singleton. And Flicker says that if pi is distinguished, then it is conjugate self-dual. So that is what the conjecture is, and in this case there's no L packet. I mean it's true. And also, what about this precise formula for the dimension? Here it's a multiplicity 1 situation. Multiplicity 1 meaning dimension home h pi comma 1 is less than or equal to 1. It's either not distinguished, or if it's distinguished, there's exactly one linear form up to multiplication by scalars. Matrange's result is a characterization of distinction in this context for generic representations. Okay, so we will assume that pi is irreducible generic. And yeah, so I just need to introduce one notion. So let me do that here. I must also say that this base change, everything is in terms of, so remark here is base change, etc. This conjecture is in terms of Landlands parameters. I mean in this formula, etc. So let's say rho pi is the Landlands parameter of pi. So rho pi is let me just say rho. Rho is conjugate self-dual. So here rho sigma would mean rho sigma of G is rho of sigma inverse G sigma. And then there is a notion of, so conjugate self-dual representations come in two flavors. So what is called parity. Parity can be +1 or -1. So on this picture, what it says is, so you have rho dual is rho sigma. So on rho cross rho sigma, you have a bilinear form, a non-degenerate bilinear form. And so that means pi of rho G rho G sigma, so VW is B of VW.
Rho is
irreducible.
But then pi is not superpositional.
No, yeah. So pi is irreducible, rho can be anything. Okay, so we will say that, so if we will say that this rho, which need not be irreducible, is of parity +1 or -1 if there is a non-degenerate bilinear form on, which would be automatic if it's irreducible, but even otherwise, so non-degenerate bilinear form such that this is true, and it's about, now it's like symmetric versus alternating. Rho G, no, B of V comma W is B of W comma, let's say rho of alpha square V, where so this is happening at the level of the Weyl group, right? So if alpha is any element outside WE, of an element of WF outside WE, and then this will be, there will be a sign here, so let's denote that sign by eta rho. Eta rho is, okay, so the parameter is said to be of parity 1 if in this formulation this is 1, and parity minus 1 if this is minus 1. So matrans result in that language can be easily stated. So if you have an irreducible generic representation, then the result S pi is distinguished, it's distinguished if and only if, so it's an irreducible generic representation distinguished if and only if it is conjugate self-dual of parity plus 1. Okay. So distinction is on the Landlands parameter side, parity being plus 1. And the result of Mach, which is about base change from UN, yeah, maybe here itself I should have said opposition group, etc. I defined somewhere. The most basic picture to remember is if G is GLN, then the opposition group is UN. And if G is UN, the opposition group is GLN. So this is the most basic picture to keep in mind. So this philosophy would say that if it is distinguished with respect to GLN-F, it should be base change from UN, right? And that is what Mach's result would say. So from UN to GLN, so let's define UN. UN is a unitary group. G in GLN-E says that G transpose sigma is J, where J is 1 minus 1, 1 minus 1, etc. Alternating 1 and minus 1 on the anti-diagonal. And a parameter for UN would be a homomorphism from WF, actually the Weil-Deligne group, to the L group of UN, which is GLNC semi-direct product WF, where what is the action of WF on this? You project to Galois of E over F, and sigma, the Galois element sigma acts by sigma of J is G transpose inverse J inverse, this J. Okay, and base change in terms of Langlands parameter. So base change from UN formulated in terms of Langlands parameter would be, so base change will be, so let's say phi of UN is all such rho. There's a technical condition. I mean, these are homomorphisms which are quote unquote admissible, and that's what one is considering, and there is a standard equivalence relation which is conjugacy in GLNC. So you consider up to that equivalence the Langlands parameters, and let's denote it by phi of UN. Then base change from UN to GLNE in terms of Langlands parameters would be a map from Langlands parameters of UN to Langlands parameters of GLNE. What is this? This is all rho from WF prime to WE prime to GLNC. GLNC is the Langlands dual of GLN. Yeah, so this is what is called, so there are two base changes in this theory from UN to GLN called the stable and unstable. What I have written down is, what is a base change map? So let's write down the base change map. If you take a parameter rho, then it is, so this is a map from WF prime, you just restrict it to WE prime. Right? Take a parameter of UN, WF, and you need a parameter from WE prime to GLNC. You just restrict it's just a restriction on the Langlands parameter side. This is the standard base change, what is called the stable base change. And then Mach's result is, so if pi is irreducible generic Maybe you don't need generic, but let me state it for generic. Take the Landlands parameter of pi, so of GLN consider its Landlands parameter, and this is in the image of base change. Base change is this map, if and only if it is conjugate self-dual pi is, or rho pi is conjugate self-dual of parity plus 1 if n is odd, and it is conjugate self-dual of parity minus 1 if n is even. Okay, so distinction is conjugate self-dual of parity 1, that is Nadir-Matrans result, and base change from a given representation is base change from un depending on n odd or even. It's either parity plus 1 or parity minus 1. But the point is, by putting these two things together, you have related distinction with base change in a precise way. So in the theory there is a notion of stable and unstable. Parity minus 1 would be what is called unstable base change, and parity 1 is stable base change. And putting this result and that result together, it says that a representation, irreducible generic, is distinguished if and only if it is in the image of stable base change when n is odd and unstable base change when n is even. So all these things are understood for GLN, and I stated this result of flicker that it's a multiplicity 1 situation. So there's nothing much to do here. The precise formula is constant 1. Okay. But before doing, I want to, yeah.
You have not introduced what is unstable base change.
I did not write it down.
So this is image of base change is unstable?
No, the base change that I introduced is stable base change. And stable base change, yeah, if it's in the image of stable base change, then it's parity 1 or parity minus 1 according to n odd or even. If I introduce unstable base change, will be the stable base change twisted with a character whose restriction is this quadratic character omega e over f. But in terms of that, this thing would say distinction is parameterized, distinction is characterized by stable base change or unstable base change depending on n odd or even. I haven't written it down. Okay, so the last part of this thing was the precise multiplicity, and it was Flicker's result from 1991 that this answer is 1. Okay, but there's another way of formulating that number 1, which is that dimension h home pi comma 1. This answer is 1, but that's not the way we would like to write it. The observation here is, it's a fact from GGP, the book GGP, which is that this map is known to be injective. Right, we would like to have the multiplicity formula in terms of base change information. The number 1 does not have base change information. So the point is, the observation is this base change map in the corresponding base change map here is injective. In other words, 1 is the cardinality of the fiber of this map. Okay, so this is cardinality of the fiber of rho pi. Right? If you have a pi here, take the corresponding Landlands parameter, which is here, take the inverse under this map, and if pi is distinguished, otherwise it's 0. Okay. So the precise formula for general groups is a bit complicated, but the essence of the formula is dimension of this space of invariant linear forms should have something to do with the base change map. How? Via the cardinality of the fiber. And depending on the group, you may need to do a bit more. Okay. So in the GLN case, it's precisely true. The dimension is exactly the cardinality of the fiber. And what we have proved recently, last year, so theorem with Dipendra Prasad, is the case when G is SLN. So in the SLN is the simplest example where non-trivial L packets do emerge. So this conjecture, one can actually test it out. There's something which is slightly non-obvious, and what we prove is this conjecture is true.
The way you stated it, you don't use any quasi-split proof for G under L?
Quasi-split was used only for this part. Otherwise, it was stated without that assumption. Genericity. So since, anyway I was going to talk about GLN and SLN, I put quasi-split at the starting. But only for this part quasi-split is required. This part is without that assumption, any reductive group. So just to give a little bit more to this statement, here what will be the corresponding situation for SLN? It will be base change from SUN, right? So one will be considering Langlands parameters for SUN. The map is to Langlands parameters of SLNE.
But I mean the group G prime underline is defined for any G.
I think it's defined for any G. I don't think quasi-split is required for that. Quasi-split is not required for that, no? Yeah. So this is the at the parameter level, this is the base change that we need to consider, and the way to prove this is, so SLN, there is one advantage, which is that L packets can also be understood in terms of GLN representation theory. So an L packet of SLN is nothing but you take a representation of GLN and restrict to SLN, and it will be a direct sum of representations. That collection is an L packet. So this extra thing that we have, we can make use of, and one can look at the GLN theory, which is in terms of base change from UN to GLNE. So the L group for this is PGLNC for SLN, and here it will be the Weyl form, PGLNC semi-direct product Weyl group. But the point is, from this to this you have projection, GLNC to PGLNC projection. From this to this you have GLNC to PGLNC projection, and the base change here, this fits into a commutative diagram. And this diagram is what one makes use of in order to prove the conjecture. But there are some subtleties involved. For example, inside now there are non-trivial L packets, and this part of the conjecture would say genericity is in terms of distinction is in terms of genericity with respect to the correct kind of additive character, correct kind of character of the unipotent radical. Yeah, so I won't get into more details because I want to mention another result. But the basic things which will solve the problem is the following three observations to start with. One is, I already stated, this is injective, and GLNE to SLNE at the level of parameters, this map, this is surjective, which amounts to saying, so this is a second cohomology vanishing result. In terms of representation theory, what it says is, if you have any representation of SLNE, it comes in the restriction of a representation of GLNE. So that is the surjectivity of this, and this is also surjective. So in terms of representation theory, if you have any representation of SUN, it comes in the restriction of a representation of UN. So these three things can be proved. And now the key observation is, so if you want to say that the dimension, if you have a representation of SLNE, you want to say that the dimension home pi 1 is exactly equal to, so let me call this, let's say PF, PE, this is the base change map, and let's denote this by PBC, right? And what one has to say is, if pi is a representation of SLNE, that dimension is the cardinality of the fibers, cardinality of the fiber of this particular map. This is what the theorem should say, will say. Yeah? So only the main point is to notice the following. So so one wants to know what kind of representations go to the same representation, right? Cardinality of the fiber. Given one representation here, what all representations can go to that? It's a many to one map, and one wants to count that. So if you start with a representation here, this is a commutative diagram, and if one starts with a representation here, this is surjective, lift it here, right? And it base changes to this. So the point is, if you have a representation here, and you can restrict it to SUN, given a UN representation, you can restrict it to SUN and ask the question, what all other representations of UN will restrict to the same representation of SUN? So this will be character twists, and these characters are characters of U1, right? It's for UN. So these are characters of U1 essentially, and so such a character, when it base changes, so if you have a U1 character chi, its base change to E star, GL1E will be some character chi tilde, which has the property that its restriction to F star is 1. Right? It will be some kind of chi tilde inverse, chi tilde sigma kind of a thing. So restricted to F star will be 1. So if you take a representation here, take its pre-image here, it's surjective, take one element in the pre-image, and if you base change here, that representation tensored with any such character, a character of E star by F star. On F star it is trivial, right? All those will have the property that they are all the same representation here, right? That's clear, no? If you have something here, that tensor with a U1 character goes to the same thing, and at this level a U1 character is nothing but a character of E star by F star. So if you take a representation here and takes anything in the pre-image, and if you base change of that tensor, any character of E star by F star, all amount to the same representation here. And what amounts to the same representation here is just twisting by characters without any further condition. So there's a difference between twisting by characters of E star by F star versus characters by E star. That's what comes out of this diagram. So one introduces a notion. So if pi 1 and pi 2 are two representations of GL and E, and this notion comes out of the analysis of that, you say that pi 1 is weakly equivalent to pi 2 and pi 1 is strongly equivalent to pi 2. This is if pi 1 and pi 2 differ by a character of E star. And this, the stronger condition, which is pi 1 is pi 2 tensor chi, where chi is a character of E star by F star. Okay, of course this implies this. So the strong equivalence classes, weak equivalence class is divided into a number of strong equivalence classes, and what this analysis tells you is the fiber of this map is the number of strong equivalence classes in a weak equivalence class. So for the right hand side of this conjecture, this part, this precise formula we want to say is fiber of the base change map, and that is a characterization in terms of these equivalence classes. The fiber is nothing but the number of strong equivalence classes in a weak equivalence class, and but these are for, okay, though I stated for pi 1, pi 2 of GL and E, we are dealing with Langlands parameters. So in this definition, everything is with a rho pi 1, rho pi 2, etc. Right? It's all for Langlands parameters, but the same definition. You can introduce the same definition as here for GL and E, and then the next thing to observe, so that's again a small preposition, is that the left hand side, the dimension of the home space is number of strong equivalence classes in a weak equivalence class on the GLN side. So the result is proved by on this side, cardinality of the fiber of the base change is understood in terms of number of strong equivalence class in a weak equivalence class of a Langlands parameter. And left hand side, the dimension, the multiplicity is number of strong equivalence class in a weak equivalence class of a GLN representation. And appeal to local Langlands conjecture, which would say that this is just twisting by characters. So that will give the equality. There is also this part, understanding distinction. Yeah, so that will only say, base change will not see inside an L packet. Base change will only see the whole L packet, right? And you need to probe inside the L packet which are distinguished, and what the conjecture says is it's in terms of psi genericity for the correct kind of psi. So how does one conclude that here? Again, GLN theory is helpful. So for GLN E, GLN F, if pi is a generic representation, irreducible generic representation, which means it has a Whittaker model. So let's say W pi comma psi, where psi is the correct kind of character. Psi is a character of NE by NF you take. You are taking psi generic with respect to this kind of a character. Then on the Whittaker model, one can explicitly write down a GLNF invariant linear form. So many groups, one cannot write down a specific formula for the invariant linear form, but this is a situation where one can write down the invariant linear form, and that's given by, so let's say L. So W going, so L of W equal to integral of WP dP P of F by N of F. So what is PF? P is the metabolic subgroup. PF contained in GLNF is matrices of this form, GLN minus 1 star 1 0 0 etc. Right, it's like the GLN minus 1 cross GL1 borel, except that this is 1 here. So it's what is called the metabolic subgroup. So you just so if you take a Whittaker function and integrate on the metabolic subgroup quotiented by NF. So this was considered in the work of Flicker. This integral is already there in the work of Flicker from late 80s, when pi is unitary. Also assumed, also if you know that it is unitary, and more generally this still makes sense by a regularization, and that is my work with Medrange in the non-unitary case. So you have a candidate, and you have a good candidate, but there's nothing obvious about it, right? First of all, it's not obvious that this is a non-zero linear form. Okay, but that can be more or less easily done. One can show that this L is not identically zero. So that's the first observation. So you have a non-trivial form, but you don't see GLNF invariance at all. It's integrating with respect to the invariant measure on PNF. So that this is invariant for PNF is obvious. You're integrating on PNF, but GLNF is a slightly bigger group, and invariance under that is not clear. But what one knows is, so L is, one knows that L is a non-zero form, so that's good. It's clear that L is PNF invariant. That's obvious. But then the result is L is GLNF invariant, so it's a bigger group than that. Precisely when, if and only if, pi is distinguished. Of course, the theorem is this part, right? If the GLNF invariant, of course, it's distinguished by the definition, and if it is distinguished, then one shows that this obviously PNF invariant non-zero form is actually GLNF invariant. If pi is distinguished, the obvious PNF invariant non-zero form is GLNF invariant. There's some work to be done. It's not obvious. It basically boils down to a multiplicity one result for PNF invariant spaces. Yeah. I mean that's equivalent to that, and that has to be shown, which requires some Bernstein-Zelewinsky derivatives, etc. So you have this candidate, and this candidate that this is the GLNF invariant form settles the matter when you come down to SLN. So this Whittaker function is written with respect to the correct kind of psi, and that's how you get the invariance under unipotent or whatever. And this settles the matter in order to probe inside an L packet at the SLN level. because at the GLN level, this is the distinguished invariant linear form, the invariant linear form, and the SLN L packet is nothing but restriction of a GLN representation to SLN, right? So one has to just check whether this, so if, and among these representations for SLN, some will be psi generic for the correct kind of psi and some others will not be. But if something is not psi generic for the correct kind of psi, this will vanish identically. Okay, so essentially, I mean, there's a small argument to be given, but essentially this is what solves the problem. So what is solving the second part of the conjecture is the precise information about the, we know it's a multiplicity one situation, so there's exactly one up to multiplication by scalars, and that can be written down explicitly on the Whittaker model is what is solving the second part of the conjecture. Now, so the basic theme that I wanted to underline was in some specific cases like GLN or SLN, the relationship between distinction and how the base change information comes in this picture, right? And we have seen for both for GLN and SLN and conjecturally much more generally that distinction is characterized by base change, and even this formula, though I haven't written down, is in terms of the base change, and for both GLN and SLN, so it's exactly the cardinality of the fiber of the base change map. So base change does appear in distinction problems. I want to take this theme, and this is somewhat unobserved before, so somewhat of a new phenomenon, where again in a distinction related question base change shows up. One cannot say unexpectedly because the philosophy is to expect that. Yeah. So we have all the general theory is about all irreducible admissible representations, but for these results we have already focused on the subclass of generic representations, where we know that this L is the distinguishing linear form, PF by NF. Right, on generic representation, on this subclass, one completely understood, everything about distinction is understood. One is writing down a specific invariant linear form. For the next result, I need to take a further subclass of discrete series representations, square integrable representations. See, though one integrated on the smaller subgroup of mirabolic, there was a natural candidate to consider, right? If you are interested in a GLNF invariant linear form, why integrating on PNF? Why not integrate on GLNF itself? Right? With respect to an invariant measure on GLNF, why not integrate straight away on GLNF? So one can try that. WG DG on GLNF by NNF. For convergence purposes, you may have to mod out by scalars, the center. So one can consider this integral. Now what I want to say is the relationship between, this will be the obvious candidate to write down. Then GLNF invariance would have been automatic because you are integrating on GLNF. The problem is this could be identically zero. This need not be, one doesn't know that this is always non-zero. You want a non-zero invariant linear form. So in this case, so in that particular candidate, non-zeroness was obvious, GLNF invariance was not obvious. In this candidate, GLNF invariance is obvious, but non-zeroness is not obvious, and the result is lambda is not identically zero precisely when, first of all, this doesn't make sense. So there I said for that particular thing, if you have any generic representation, this makes sense. As I said, in the unitary case, this goes back to mid-80s, and in the non-unitary case, a bit of regularization is required, and still this makes sense, and that's more recent, but this makes sense. The integral converges, or some regularization makes sense. In this case, the integral is not well defined, it doesn't make sense, but that's why I'm going to this thing. So it's a result of Cable, 2004, that if you consider the subclass of discrete series representations, this integral makes sense. It's well defined. It's a convergent integral. So in this subclass, so in this class we considered that invariant linear form, and that linear form which is invariant precisely when distinction is there. And in this further subclass you have another natural candidate, right? Among the discrete series representations you have another natural candidate, and that is obviously GLNF invariant, but it could be identically zero. It's not identically zero precisely when pi is GLNF distinguished. Theorem being this way, other side is obvious. No, theorem being this way. Right? If you have a discrete series representation which is GLNF distinguished, then one can show that this is not identically zero. So the summary of these two things, so there are two natural candidates in the discrete series class. One is integrating on the parabolic, which has the property that non-zeroness was obvious but not the GLNF invariance. And you have this other candidate for which GLNF invariance is obvious but non-zeroness is not obvious. Right? But non-zeroness here and the GLNF invariance here happens, one knows, precisely when pi is distinguished. So if you consider pi irreducible discrete series, so that both invariant forms one can consider, discrete series and distinguished, so that you have all the properties. Then you have two non-trivial invariant linear forms. Two non-trivial invariant forms, lambda and L. Both lambda and L are now, things that you can consider. Both are non-zero, both are invariant linear forms, right? But we know it's a multiplicity one situation. We are GLNA, GLNF, so these two should differ by a scalar, right? So lambda will be a scalar, of course, depending on pi times L by multiplicity one. So the next result is more recent with Nadir-Matrand. What can one say about this constant C pi? Two natural linear forms come and they differ by a scalar, what one can say. And what was the general theme of the lecture? Distinction is related to base change, and that's what, and we know from Mach plus Nadir-Matrand put together that distinction is base change from UN, and here you have a discrete series representation which is distinguished, so it will be, this pi will be base change of a representation rho of UN from Matrand plus Mach put together. It's not a packet, it's a singleton because pi itself is discrete series. There's no, the base changing one is known to be a singleton because the starting representation is not any irreducible admissible but discrete series. And the result is this C pi is a constant, let me put a square, but this constant is a measure theoretic constant. So it's not so important because all these integrals, some measures involved. As you change the measures, this constant can change. This has nothing to do with the representations. It's a purely volume computation constant times L, and this is the significant part. It is, so corresponding to pi, it's base change from rho, and it is d pi d rho. So this constant is a nice constant, and it is d rho by d pi. What is d rho and d pi? D rho is what is called the formal degree. D rho is a formal degree of rho, and d pi is the formal degree of pi. So these are all infinite dimensional huge representations. Formal degree is something which is like the dimension for a finite dimensional representation. Okay. So if you write down for finite group representation theory, if you write down the orthogonality relation for not characters, orthogonality relation for matrix coefficients, there will be a dimension coming in, and if you write down just change the sum by integral, that orthogonality relations, what the number that appears there is called the formal degree. So it's, yeah. No, yeah. Lambda is C pi times L and C pi is this constant. Yeah. So what this shows is in a completely new way, again in a question which is very much related to distinction, right? You have two invariant linear forms that differ by a scalar, base change information appears. That pi is, right? This side has nothing to do with rho. Rho is not there in the picture at all here. But when you write down this, in this constant, the base change information appears in terms of formal degrees. I have 2-3 minutes, so maybe I will just say very quickly what goes into the proof. It's okay. So for us, this proof, for us, this comes kind of free, but that doesn't mean proof is easy in the sense we are, putting various things from the literature together. So the ingredients are the first ingredient is the Rankin-Selberg theory. Rankin-Selberg theory of the SIL function, the local SIL function. So this is due to Flicker, mid-90s, maybe 94, and also Cable in a much more modern way, 2004. So this is the first ingredient. So what this would say is you will have a local functional equation for the SIL function, etc. So there are two sides of the functional equation with a gamma factor coming in. And what one can do is do some manipulation so that on one side of the functional equation you can manipulate to get to L, and on the other side of the functional equation you can manipulate to get to lambda. There's something to be done, but then on one side you will see something like lambda, on the other side you will see something like L from this theory. What comes in there is what is called the SI gamma factor. Okay? And the SI gamma factor is related to the gamma factor for the tensor product in a very precise way. And the second ingredient is, but I don't have gamma factors here, but the formal degrees here. And that is the Hiraga, Ichino, Ikeda, Hiraga, Ichino, Ikeda formal degree conjectures. So I need this conjecture in two cases, one for GLN and one for UN. This is for any group, the conjectures. And for GLN, the conjecture is already a result due to them, HII. This is 2008 when the conjecture is formulated. In the same paper, they proved the result for GLN. So these conjectures would say that the formal degree of a discrete series representation can be written down in terms of the modulus of the gamma function, the adjoint gamma function evaluated at 0 with some constant. Constants won't matter for us. So for GLN, it was already done. And when we first had the result, it was assuming the conjecture, but after our submitting the paper, this was also proved. So this is very recent, and this is proved in 19 by Boussaplassi. So that will relate, from here you get a gamma factor. That gamma factor can be related to the adjoint gamma function coming for UN divided by the adjoint gamma factor coming for GLN, and then when you appeal to the formal degree conjecture you will get something like that up to modulus, and then you need a trick to get rid of the modulus. While getting rid of the modulus, there will be one more thing coming here, which is a certain epsilon factor at half pi SI psi. But I did not write that down there because again there is a recent result of Boussaplassi which says that in our case situation that we consider it as 1. So that's another non-trivial input. Otherwise the result would have been epsilon times d rho by d pi. But that also is known to be 1. There's one more ingredient which goes into this, which is also not obvious, is that there is this kind of an equality, W tilde P over P by N equal to WP dP over P by N, where W tilde is the Whittaker function on the contragradient of pi given by W of W G transpose inverse, where this is the longest file element. A specific thing. Once again, that these two differ by a constant is not difficult to see, but that precise constant is 1 is something very non-trivial, and that is an earlier result of mine with Matrange. 2017. And that also is non-trivial in the sense there also there is a local root number coming, which is the Rankin-Selberg root number for the tensor product. So here there is a root number, here there is another root number, both turn out to be 1. So all that has made the final formula simpler. Those are non-trivial inputs, and this is the most non-trivial input. the formal degree conjecture for GLN and UN. UN is recent, and that's B surplus A. I think I have taken all the time, but just to conclude by giving an elementary situation just to illustrate how this result goes, one could have asked what happens for finite fields, right? I mean, these are all periodic fields. You have such a result. So what will be the analog of lambda and L? L will be summing over the mirabolic. F is now finite field. Let's say FQ of WP, right? And lambda is summing over GLN FQ of W, let's say G, where pi is a representation of, irreducible representation of GLN FQ square. Right? So this is obviously GLN invariant now. There's no convergence question. It's a finite sum, and but it could be identically zero. This is, one can show, is not identically zero, but it's not GLNF invariant. So one can put oneself in a situation. So if you know that dimension of PNF fixed vectors is 1, this is not the case. Dimension of PNF invariance can be huge, but you put yourself in a case where this is 1, just like we restricted to discrete series. Come to a subclass, right? So this is the case, for example, when pi is a cuspidal representation, and in slightly more generally also it is true. So anyway, put yourself in such a situation, which is what is usually called relatively cuspidal. Cuspidals are relatively cuspidal. Pi is GLN FQ square. No, FQ. You are looking for distinction for the subgroup PN FQ. PN FQ invariance. Right? If you know that you are in this situation, which by definition you can take it to be this, then you know, like earlier, that this is also a GLNF invariant form by multiplicity 1. Again, for finite fields also multiplicity 1 is true. So one has both lambda and L, and one can ask for the constant, and you will expect from this thing. I told you that formal degree is the analog of the dimension, and it is true that it is dimension rho. So pi is a base change from the unitary group. Base change of rho. Rho is a representation of UN, and lambda is a specific volume constant, which is some cardinalities, which has nothing to do with the representation. Dimension rho by dimension pi L. This constant is some order. It may be GLN. Yeah, I mean it's GLN FQ square, GLN FQ UN, all these cardinalities. So it's exactly like that measure theoretic constant. And this can be proved elementarily, of course. Yeah. And anyway, there's no formal degree conjecture kind of thing. There's no gamma factor in finite field theory, but then one can do it because it's over finite fields. One can give a direct proof, and this is also joint work with Matranch. We do it a bit more generally. We do it not just for GLNFQ square, GLNFQ. We also do it for GLNFQ square UN, and more recently, I am suddenly blanking out on the name. I think Chang Yang has proved it for any reductive group G, the same formula. Exactly our methods go through with some more algebraic group inputs. Okay, I think I've overstayed. So.
Okay, if not, let's thank you.
Thank you. Yeah.
4 o'clock lecture will be the opposite.